There we go. All right, so we're going to add in one more type of sequence here. And that third type of sequence is called a recursive sequence. So our last, well, maybe not totally our last, but one of our last types of sequences is a recursive sequence. I'm going to define this with words, and then we'll go through like what it looks like in practice. So a recursive sequence is a sequence that generates each term by using the previous term or terms. So I'll just put the S in parentheses just to denote. It might just be that you only use one term. It might be that you use multiple terms. Just depends on the sequence. The thing about a recursive sequence that can make it a little tricky and a little more challenging possibly than the sequences we talked about yesterday is that in order to find like the 20th term, I have to find all 19 terms before it. Whereas yesterday, if I wanted to find the 20th term, I could just plug 20 into my sequence. So it's a slightly different type of approach. So let's just try seeing what it looks like to actually work with one. So this is our recursive sequence. The thing about a recursive sequence is you have to be given at least one term. So we're going to be given, in this case, a sub 1, the first term, is 3. Now with recursive sequences, I don't really know why they do this, but it seems like we use K instead of N when talking about the terms. So what this is saying is that if I wanted to find, let's say, the 4th term, I need to use term 4 minus 1, which is 3. I multiply it by 2 and then add 1 to that. So algebraically, I kind of want to do this, and then we'll do this with a table. I think sometimes it's easier with a table. Sometimes it's easier if you see how this is being generated algebraically. So let's say I want to find term 2. So I'm going to use this guy right here, and I'm going to put 2 everywhere I see K. Okay, so I'm going to put 2 times a sub 2 minus 1 plus 1. So I'm just replacing those K's with 2's. Let's simplify a little bit and then we'll evaluate. So what that means is I'm really using 2 times a sub 1. Now the good news is I know what a sub 1 is. A sub 1 is 3. So I can just replace this a sub 1 with 3. Remember, when we see an A, that is denoting the term in the sequence. We have to look for that term. So then evaluating this means I'm going to do 2 times 3 plus 1. So that 3 comes from what we were given. So that all just ends up being that our second term is 7. So now I know what term 2 is. Okay, so let's do one more like this, and then we'll talk about how we can do it with maybe a table approach, which is a little bit less writing, but at least you'll have an understanding of what we're doing, maybe a little bit better. All right, so term 3. Again, I'm going to put 3 wherever K is. So 2a sub 3 minus 1, and then we're going to add 1. So I'm just replacing all my K's with 3 since I'm finding the third term. Well, that means we're going to have 2 times a sub 2 this time, and then we'll add 1. And good news, we know what a sub 2 is. We found that in the previous calculation. It's just 7. So I'm going to do 2 times 7, and then I'll add 1. So that gives me 15, sorry. So now I know the third term in the sequence. So at this point, my sequence is 3, 7, 15. Now there's going to be more terms depending on how far you want to go. But again, if I ask you to find like the 12th term in this sequence, you're going to have to find 11 terms before you can find the 12th term. Now sometimes I like to do this. I like to show you multiple ways you can address this. Let's talk about what this might look like in a table. So let's just fill in what we know here. We were given the first term, the second term, or found the second term, found the third term. Let's find terms 4 and 5. So term 1 was 3. Term 2 was 7, right? I can't see that anymore. Yeah. And term 3 was 15. All right, so to find term 4, what this is telling us to do, this recursive definition here, is to take 2 times the term in front of the term you want to find and then add 1. That's what that means. So essentially, I'm going to take whatever I just found, which is 15. I'm going to multiply it by 2 and add 1. And what do I get? I get 31. That's the next term. Okay, so recursive is just saying you have to use the previous term to do all the calculations. So we got one more we can find. So now if I want to find term 5, I've got to take term 4, multiply it by 2, and add 1. Earlier today, I said that was 65. It's not. It's 63. And that's term 5. All right, so the idea of a recursive is you have to at least know the term in front of the one that you want to find. They are kind of a pain in that respect. Like you can't just say, oh, find the 100th term of that sequence, because we don't have it defined in a non-recursive manner. We could try to define this in a non-recursive manner. We could try to figure out what the pattern is in the table, but we're not going to today. That might be something we do in a future lesson, but not today. Okay, let's talk about another one. Just a continuation of this. Let's find another recursive here. This time, we're going to use one that's a pretty famous sequence. And you've probably heard the name before, the Fibonacci sequence. Yeah. So this one is a very special sequence. Okay, so here's how it is defined. We are going to be given the 0 term is 1. The first term is also 1. And then whatever term you want to find, so a sub k, will be a sub k minus 1 plus a sub k minus 2. In other words, add the previous 2 terms together. That's really what that is saying. Let's just find one by plugging stuff in, and then we'll go to the listing approach or a table approach. I'm just trying to give you some different ways that you can calculate these, some different approaches. So we'll do one where we're plugging stuff in. So let's find term 2. Okay, so we're going to plug in 2 wherever we see our k's. So that means we're going to have a sub 2 minus 1 plus a sub 2 minus 2. Again, I'm going to simplify that just a little bit so it makes it a little bit easier to calculate. So to find the second term, we're going to take a sub 1 and add it to a sub 0. Lucky for us, we were given those 2 things. A sub 1 is 1. I'm sorry, a sub 0 is 1. So a sub 1 is 1, and then a sub 0 is also 1. So we're going to be able to just add together the previous 2 terms. So to find a sub 2, we're going to take 1 and add it to 1. And that gives us 2. So now what I know is that the second term is 2. So if I start to think of this as a list of numbers, so far I have 1, 1, 2. If I want to find the next term in the sequence, this is all a Fibonacci sequence is telling us to do. It's saying take the previous 2 terms and add them together. So when we add 1 plus 2, we get 3. That's the next term in the sequence. And then we continue that pattern. To find the next term, we add 2 and 3 together to get 5. That's the next term in the sequence. Let's just do this a few more times here. We won't do a bunch, but a few. I can take 3 plus 5, get 8. That's the next term in the sequence. What comes after that? 13. One more, just for fun. 21. Yep. Good. And then we showed ... to show that that keeps on going. Okay, it's just, it's a very special recursive sequence. That's all. Named after the mathematician Fibonacci. All right. The last sort of topic I want to look at is it's really a special product that shows up a lot in sequences. And it's called a factorial. So let me see here. Yeah, that works. So the last thing I want to talk about today is this idea of a factorial. So number one, this is a special sequence, or a special product. This, if you look at it as a sequence, shows up a lot when we're trying to work through sequences. So is common in sequences. So let's talk a little bit about what a factorial is. First thing I'll do is just give you a couple of here's how you would do it, and then we'll define it in a more generic manner. So first of all, if I said 4 factorial, what that means is I'm going to take 1, starting at 1, and basically multiply all of the integers up to 4.
Or can you go the other way for factorial?
You could,
Okay.
Yep. And I'll show you that here when we start calculating some more of these. So if I do that calculation, it's 1 times 2, which is 2, 2 times 3, which is 6, 6 times 4, which is 24. So 4 factorial is 24. The exclamation point is what factorial is. Okay? So that's just the notation for it. Let's go in, the opposite direction. Oh, not opposite, but let's go one more here. What's 5 factorial? So you pointed out we could do this in the opposite direction. Absolutely. You can start at 5 and you can count down all the way to 1. And either one is fine. Okay, it just doesn't matter which way you do it. Essentially, if you're observant, you'll notice that 1 times 2 times 3 times 4, we found just a moment ago is 24. That shows up here. So it really is a type of recursive formula, because all I'm going to do is take that 24 and multiply it by 5. And that's going to give me 120. Let me go backwards a couple here. So let's go to 3 factorial. So again, you can start at 1 or you can start at 3 and count down to 1. It does not matter. What is 3 factorial? 6. I did not leave myself enough room. What's 2 factorial? So we're going to do either 2 times 1 or 1 times 2. It does not matter. We get 2. I have room for 1, but I wanted to leave room for 0, but I'll put that off to the side here. What's 1 factorial? Just 1. Now, here's what I want to do. I want to define it using a more generic approach. So we said it's a special product. It's common in sequences. We sort of found the first few terms of it. It's defined this way. N factorial, if we define it in a generic manner, says start at 1, and multiply the numbers together all the way up to n. So whatever n is, you're going to go from that number, or from 1 up to that number. One really important thing here that we have to define is 0 factorial is always 1. It might not make sense why that is. Sometimes in math we have things that are created by man instead of discovered by man. This is kind of a combination of those two things, but we have to have 0 defined in some way, so we define it as just being 1. So if I ask you to find any number factorial, it just means you're going to take whatever that number is and count up to it from 1, multiply all those integers together. Let's just do, yeah, we got some time. Let's do a couple things with this. I'm not going to do a lot, but I want to at least talk about a couple things. This is not example 1. I think it's like 2 maybe, or 3. It doesn't really matter. Let's find, I don't know, the first, let's go 4 terms of, and I'm just going to give you just a normal sequence, okay? So it's not a recursive sequence, it's just a normal sequence, but it's going to have a factorial in it. A sub n equals 2 to the n power over n factorial. This time we want start with your first term instead of starting with n equals 0, or instead of starting with n equals 1, start with n equals 0. Normally we start with n equals 1, but I mentioned yesterday if I want you to start with n equals 0, you'll be told to. Now, I don't care how you do this. You know, you organize your thinking, whatever works best for you. I'm going to go with probably making a table again, just because for me that makes things a little bit easier. So I've got a sub n, n and a sub n. All right, so I want to find the first 4 terms, 1, 2, 3, and 4. So let's talk about the first term.
Didn't you say there was 0?
Yep, thanks. I was just thinking I didn't start with 0. Took the words right out of my mouth. Okay, 0, 1, 2, and 3. That's actually the first 4 terms, right? Since we start with 0, there's 4 terms there. Just happens to be that we only get up to 3. All right, so let's start with that 0 term. Plug in 0 for n. I'm going to do my calculations off to the side here. So 2 to the 0 over 0 factorial. What is 2 to the 0? Just 1. Yep. What is 0 factorial? Also 1. So this just simplifies to be 1. So our first term is 1. All right. 0 term is 1, I guess. Let's find term 1. So I'm going to plug in 1 for n. So 2 to the first power divided by n factorial, which I didn't put the 2 in there, 2 factorial. 2 to the first power divided by 2 factorial. Okay, 2 to the first power is 2, right? Anything to the first power is just itself. 2 factorial is?
Isn't it? Wait, are we on 2 or are we on 3?
Gosh, we're on 1. Why am I writing? What am I doing, guys? Let me try that again. That's a 1, isn't it? 1 factorial. There you go. I'm having all kinds of problems. Okay, so that's just over 1. We get 2. So term 1 is 2. All right. Maybe I can get this one right without any mistakes. Okay, term 2. Plug in 2 for n. So that's going to be 2 squared over 2 factorial. All those 2's. It's confusing my brain. What is 2 squared? So that's 4 over 2 factorial, which is 2, and we get 2. We'll do one more, and then we'll stop here. I just want us to get used to this idea of how to use a factorial in a sequence. All right, last but not least, we've got 3. So I'll do 2 cubed over 3 factorial. So 2 cubed is 8. Over 3 factorial is 3. So just 8/3?
Why don't you do 3 times 2 times 1 for 3 factors?
Yep. Is it Monday? Holy cow.
Isn't it Tuesday?
I know, but it feels like a Monday with all the mistakes I'm making. 8/6, so that's 4/3. Holy mackerel. I did better first period when I did this in my head. Not writing stuff down, I actually did better with this. All right, so the terms of this sequence are sort of interesting. If we write them out here, we've got 1, 2, 2, and then 4/3. If I asked you to try to figure out what the generator was and gave you that sequence, 1, 2, 2, 4/3, that would be rather challenging. One of the things that you can start to think about when you see some that don't look like there's a pattern involved is to think about the possibility that maybe you're dealing with a factorial, because those factorials kind of throw off all of your other patterns. And I want to just take one moment and go back up to what we saw in those factorials. So if we look at the first 5 terms of factorial, or first 6 terms, we'll just say first few terms. Okay, we have 1 as the 0 term, 1 as term 1, and then we have 2, 6, 4, 120. I wrote that because if you start to see that in a sequence, then you know you're dealing with a factorial. 24, not 4. So you have this capability of recognizing now a factorial when it's present. So watch out for that pattern. It shows up a lot. In fact, it's going to show up more than once on your homework tonight. So that's one that if you look, if it were me, I'd probably highlight that little first few terms thing, put a big circle around it, something, make it stand out, because that's one that you're going to see show up in sequences quite often. Hi. One more kind of quick thing, and then we'll be done. I said I wanted to do a couple more things with factorials here. Okay, so let's just play around a little bit with simplifying. Factorials. So let's say I ask you to simplify 8 factorial over 2 factorial times 6 factorial. Now your gut is saying, oh, well, the 2 and the 6 add together to make 8, so that's just 1. Not quite. And I want to show you how we can do this kind of a long way, and then maybe you'll start to notice some shortcuts that you can take here. Let's think about this. 8 factorial is 8 times 7 times 6. I'm going to write it all out here, all the way down to 1. And we're dividing that by 2 factorial, which is 2 times 1, times 6 factorial, which is 6 times 5 times 4 times 3 times 2 times 1. When I write it out that way, it's really hopefully apparent where these giant ones are going to be. Right? I've got a giant one here, and then here, and here, and here, and here, and here. And I even have, if you think about 8 over 2, I could simplify that as well. If you maybe didn't see that and you just went and said, okay, well, that's 56 over 2, hopefully you recognize that 56 over 2 can be simplified to just be 28. So that factorial expression, we didn't have to touch our calculators to evaluate it. We could just use some simple simplifications. But what if I throw in variables? So what if I give you something like this? Simplify n factorial over n minus 1 factorial. So now we're making it more generic. Now I want you to think about when I wrote out 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, I could have written it like this. I could have written it as, okay, 8 times 8 minus 1 times 8 minus 2 times 8 minus 3 times all the way down to 1. Right? Because 8 minus 1, that gives me 7. 8 minus 2 gives me 6. Do you see that? I can do that with my n. Same kind of idea. So I'm going to think of this as I'm going to multiply it n times, and then I'm going to subtract 1 from n. And then I'm going to subtract 2 from n. And then I'll subtract 3 from n. And I'll keep doing that until I get down to just 1. Okay, that's exactly what we're doing when we're doing a factorial. We take whatever the number is, and we keep subtracting a number from it, all the way down to 1. Okay, so then let's look at n minus 1. So we start with n minus 1. That's my first term. And then I'm going to subtract 1 from that, so I get n minus 2. And I'm going to subtract 1 from that, so I get n minus 3. And I keep doing that until I get down to just 1.
What do you mean getting down to just 1?
So when we're doing a factorial, remember we're reducing this number by 1 all the way down to just 1.
Equals 1.
And yes.
Okay,
Yeah. Yeah. So we keep going until we're all the way down to whatever 1 is, or when we get down to 1. All right, now at this point, we do it that way, and I wrote it that way so we could find our giant ones. Okay, we've got a giant 1 here, a giant 1 here, a giant 1 here, and everything between n minus 3 and 1 will also be a giant 1. Right? Because I'll have n minus 4, n minus 5, n minus 6, all the way down to whatever I get when I get down to 1. So we have a whole bunch of n minus 1s, or n minus whatever, getting us down to 1. So the only thing that's left in this expression is what? N. This is a nice, if you recognize this happening, this is going to make simplifying these factorials super simple. So like if I gave you 7 factorial over 6 factorial. This is n. This is n minus 1. Right? If n is 7 and we subtract 1 from 7, we get 6. So it would just be 7.
Wait, can you explain that again?
Yep. So n is just any number we want it to be. Okay. So in this situation, I want n to be 7. So if I take 7 and I subtract 1 from it, I get 6. So it fits this pattern that we talked about up above, right? Yeah. So it's part of this same kind of approach. And this whole thing simplifies to just be n, whatever's in the numerator in this situation. So it's an easy way to simplify that without having to go through all of the giant ones. So today we talked about a couple of things. We looked at recursive sequences. We looked at this idea of a factorial, both of which can help you when you're looking at different types of sequences. So you'll have some practice with those tonight. I think tonight you're going to be doing some just listing of terms. You're going to be writing some sequences, and I don't think I'm having you write recursive sequences. I need to double check that. If I am, I think you can handle it. And then some stuff with factorials. Okay? Do you guys have any questions?